So between 0 and 2, the graph of the absolute value looked just like the regular x cubed minus 5x squared plus 6. Then from 2 to 3, it looks like the negative of that, x cubed minus 5x squared plus 6x. And then from 3 to 4, it looks like the positive of x cubed minus 5x squared plus 6x. Okay? So that's why you have to break this one up into 3 pieces. Now, with a linear one like we did before, just the absolute value of x, you only have to break it up into 2 pieces. This right here, this was the graph negative x, so that's why we integrated it from negative 2 to 0. This right here was the graph y equals positive x, so that's why we integrated it from 0 to 2. Alright, and that's because the original, that's why we start at negative 2, is because the original problem was from negative 2 to 2. So we start at negative 2, we break it up, we end at positive 2. This one, you end up getting 6.116 repeating, or 6 and a 6th. The ability to actually do those definite integrals is pretty important. It's so important, it's actually called the fundamental theorem of calculus. Okay, so an integral from a to b of a function f of x dx, you integrate this capital F, this is the integrated answer. The integrated answer evaluated at b minus the integrated answer evaluated at a. You know, and that sounds pretty important, the fundamental theorem of calculus. It is. Okay? So that's what we've been doing, you know, for the past 2 days, or yesterday and today. Pretty much it's just definite integrals. So we've already been using the fundamental theorem of calculus. We just didn't know. One thing that students will sometimes get a little confused is that they'll want to put plus c. We put plus c when we do indefinite integrals. That's where we don't have the boundaries. So like, there's a difference between the integral of secant squared of x dx and the integral of secant squared of x dx from 0 to pi over 4. Okay? While at first, initially, we do get the same answer, we know that the integral of secant squared, we don't do a little trick with the power, do we? We know that the integral of secant squared is tangent because the derivative of tangent is secant squared. So the integral of secant squared is tangent. And if it's an indefinite integral like this, we learn that you put plus c. So the integral of secant squared is tangent of x plus c. But if we do a definite integral, then we say, okay, that's equal to tangent of x. Then we evaluate that using our boundaries. We say from 0 to pi over 4. And so that's the tangent of pi over 4 minus the tangent of 0. or 1 minus 0, which is 1. So that's the difference between an indefinite integral and a definite integral. Let me do a slightly easier absolute value integral. Let's look at the integral of the absolute value of 2x minus 1 from 0 to 2. So it's real easy to write down what the absolute value of 2x minus 1 is actually what it's equal to. Alright? It's going to be 2x minus 1 as long as x is greater than or equal to what? It's going to be equal to the original function as long as x is greater than or equal to 1/2. It's going to be equal to the negative of the original function as long as x is less than 1/2. Why 1/2, you may ask? Well, if we were to think about the graph, let's graph y equals 2x minus 1 really quick. So y equals 2x minus 1. We're not going to have these negative answers down here, or these negative points down here. We're just going to have the positive ones. But I'm going to draw it anyway, and I'll show you what the graph looks like. 2x minus 1 crosses at negative 1 and then has a slope of 2. So it's up 2 over 1, up 2 over 1. Okay, so it goes about like that. The negative of 2x minus 1 would have a y-intercept of positive 1 and a slope of negative 2. So if I was just to draw y equals 2x minus 1 and y equals negative of 2x minus 1, I get those two graphs. Well, this this part here that I'm highlighting, this is the absolute value. 2x minus 1. Because remember, absolute value always gives us positive answers. So anywhere from the graph, I can trace over and I'm at a positive, positive, positive. I said only positive, but we do have one exception. There it's 0. So where is this? Where is the place where we change from this to this? Well, it's going to be 1/2 for x, 0 for y. That's why this is split up like it is. It's equal to this function here, which is this graph, as long as x is here or over. It's equal to this function here, this graph, when it's less than 1/2 on the x. Okay? So if I want to find the integral of that from that absolute value function from 0 to 2, from x's starting at 0 all the way until I get right here. What function is that? That's the negative of 2x minus 1. Okay. So integral from 0 to 1/2 what function is this again? That's the negative of 2x plus 1, or 2x minus 1, plus, what function is this right here? This is the positive of the function. And that's from 1/2 to where? To 2. For linear equations, if you want, just like that last equation, even the cubic equations, if you want to know where it touches the x-axis, all you have to do is set the function equal to 0 and solve for x. So that's 2x equals 1, so x equals 1/2. That's how I figured that out so quick. What did we have to do in this other crazy one with the cubic? The places where it touched, remember, we had to factor, and then we could figure out at 0, 3, and 2. This one wasn't quite that complicated. Alright, so let's finish this one up. So that's going to be the negative of the integral of 2x. It's going to be x squared divided by 2. So that's just x squared. What's the integral of negative 1? Negative x, right? Because the derivative of x is 1. So the integral of 1 is x. Alright, and I'm evaluating that from 0 to 1/2 plus this integral right here. So that's going to be what? X squared minus x. And I'm evaluating that from 1/2 to 2. Alright. So that's the negative of 1/4 minus 1/2 plus, oh, well, I don't want to skip anything. Minus what? What happens when I plug in 0? I get 0 for both of those. Plus, plug in the 2. It's going to be 4 minus 2 minus, now plug in the 1/2. It'll be 1/4 minus 1/2. Alright, so that is 1/4 minus 1/2 is a negative 1/4. That negative in front will make that a positive 1/4. And then plus 2. And then that's going to be a negative 1/4 again. But there's a negative in front, so it's going to be plus 1/4. So that's going to be 2 plus 1/2, or 5/2. Alright, so let's take a look at a few definite integrals, just to make sure that we have the hang of that. Because even if we know how to evaluate a definite integral, sometimes we have to just be able to evaluate the integral to do the definite integral. So that's the tough part. Let's start off with a fairly simple definite integral. The integral from 1 to 3 of 4x cubed minus 3x squared dx. So I want to integrate these two terms using the power rule. So that's 4x to the 4th divided by 4 minus 3x to the 3rd divided by 3. All that will be evaluated from 1 to 3. The 4's cancel out, the 3's cancel out, and all I really have is x to the 4th minus x to the 3rd. So I'm going to plug a 3 in. 3 to the 4th power is 81, minus 3 to the 3rd power is 27. So I plugged in the top boundary, then I say minus, plug in the bottom boundary, plug in a 1. 1 to the 4th is 1, minus 1 to the 3rd is 1. Alright, so 81 minus 27, that's going to be 54 minus 0, so just 54. Alright, let's look at this one. The definite integral from 1 to 8 of the square root of 2 over x dx. One like this, you have to rewrite it first. Remember, the square root of a fraction, say the square root of a over b, that's equal to the square root of a over the square root of b. So this would be the integral from 1 to 8 of the square root of 2 over the square root of x. And anytime you have a constant with an integral, you can just take that constant out in front of the integral. So this is the square root of 2 times the integral from 1 to 8 of 1 over x to the 1/2. Well, we can't integrate that like it is. We can't apply the power rule. We need this to be in the numerator. So that's equal to the square root of 2 times the integral from 1 to 8 of x to the negative 1/2. And so now we can apply the power rule. When I add 1 to the power right here, that power becomes positive 1/2. Alright, so this is the square root of 2 times x to the positive 1/2, and you divide it by its new power, positive 1/2. Add 1 to the power, divide by the new power. That's what I did right there. Now this part, it has to be evaluated from 1 to 8. So this is the square root of 2 times, if I flip and multiply that, that's 2 x to the 1/2, and that part is evaluated from 1 to 8. So that's the square root of 2 times, plug in an 8, that's going to be 2 square roots of 8 minus, plug in a 1, 2 square roots of 1, which I really never write because that's just 1. Alright, so this is the square root of 2 times The square root of 8 is the square root of 4 times the square root of 2, or 2 square roots of 2. So that's 4 square roots of 2 minus 2. I wouldn't say that's the most correct answer, because I can still factor something out of that. I can factor out a 2, right? So that's 2 square roots of 2 times, that would be 2 square roots of 2 minus 1. Now, depending on the problem, if it asks you for a decimal, you could find that, but the only other way to write this answer would be to multiply this square root of 2 in. That would make that 8, but you'd have 8 minus 2 square roots of 2. So potato, potato, same difference really. Alright, let's take a look at this one. For some reason, this looks like a kind of a test-like question. Maybe I've put something like this on a test before. Alright. So if I want to do this integral, this definite integral, I want to evaluate it. I can't just start integrating terms because I have a product here. I have this times this. One of the things that I've told you previously was that if you integrate a fraction, you can't just integrate the top and integrate the bottom. You can't just integrate the numerator and integrate the denominator. That will give you the wrong answer about 99.999% of the time. Okay? And it's not always, but pretty much the same if you integrate and you have a product. You can't just integrate the first and integrate the second. I have students do that all the time. All the time. And it really, really makes me cry when I see it. Know that you have to do something so that you can integrate it. I'm going to have to multiply this in to integrate this. Now, this really doesn't even have anything to do with the definite integral part. It's just to do the integrating, I have to multiply that in. So think about that like that's t to the 1/2 power. Okay, so this is going to be the integral from 0 to 2 of, that's t to the 1/2 power times 2, so that's going to be 2 t to the 1/2 minus t to the first times t to the 1/2. Add the powers, so it's going to be t to the 3/2. 1 plus 1/2 is 3/2. Okay, so I haven't done any calculus yet. All I've done is distributive property. So now I can integrate each term separately. So add 1 to the power and divide by the new power. So when you add 1 to 1/2, you get 3/2. You have a 2 in front, so this is going to be t to the 3/2 divided by 3/2 minus, add 1 to this power and divide by the new power. So that's going to be t to the 5/2 divided by 5/2. Okay. Now I do want to simplify that just a little bit, but then I need to remember I got to evaluate that from 0 to 2. The way that I simplify that is I flip and multiply the denominator times the numerator. So this is going to be 4/3 t to the 3/2 minus 5/2 Right here, I was supposed to divide by 5/2, not 2/5. I don't know why I did that. So it's going to be what? 2/5 t to the 5/2. I'd written 2/5 down here. Usually when I do that, I'm thinking ahead in my squirrel brain, and I'm meaning to write it in front, but because I don't always write it down here. And we evaluate that from 0 to 2. Alright, so if I plug in a 2 there, that's going to be 4/3, and there, 4/3 times 2 to the 3/2 minus 2/5 times 2 to the 5/2, and then minus, when you plug in a 0, you get 0 and 0. Alright, so this is probably not the best way to write this answer. You could definitely factor out a 2 to the 3/2, and that would leave you with 4/3 minus 2/5 times. So what would this have to be so that if I multiplied this back in, I would get 5/2? That would need to be 1, right? Because 1 plus 3/2 is 5/2. Alright, let me repeat that. I saw that this has 2 to powers, a base to a power. So you factor out the smallest power. When you do that for this term, this goes away from that. Minus. Now remember how this stuff works when you factor it out. I have to put an answer down here for 2 to some power, so that when I multiply what I factored out times this, I would get 2 to the 5/2 power. Remember, you add powers, so 3/2 plus 1 is 5/2. Alright, so this is going to simplify nicely. This is 2 to the 3/2 times 4/3 minus 4/5. Alright, so that's going to be 15. So I'm going to say that's 5 times 4 is 20 minus 3 times 4 is 12. So I have 2 to the 3/2 times 8/15. Or the square root of, you know what that is? The square root of 2 cubed. So that's the square root of 8. The square root of 2 cubed. So that's going to be 8 square roots of 8 over 15. You know, if you don't want to leave that like that, what can we do? That's the square root of 4 times the square root of 2. The square root of 4 is 2, so that's 16 square roots of 2 over 15. So that right there is the most correct answer. Alright, look at this integral. The integral from 0 to pi over 4 of 1 minus sine squared theta over cosine squared theta d theta. So if you try to start integrating this numerator and integrating this denominator, you might think that you could use the power rule with these trig functions, but the power rule doesn't work because that's not the type of integral it is. So you're going to have to use some type of trig identity to make this thing a lot easier. And we all notice that when we see 1 minus sine squared or 1 minus cosine squared, we have something that kind of goes off in our memory, hopefully. If sine squared plus cosine squared of theta is equal to 1, then you can move either one of these functions over. You can get 1 minus sine squared theta equals cosine squared theta, or 1 minus cosine squared theta equals sine squared theta. So I have 1 minus sine squared theta, so I need to notice that would now be cosine squared theta over cosine squared theta, or just the integral of 1 d theta. And what's the integral of 1? Just x, or in this case, just theta. So it's theta evaluated from 0 to pi over 4. Or pi over 4 minus 0, just pi over 4. Okay. So let's try the definite integral from negative pi over 3 to pi over 3 of 4 secant theta tangent theta. Now this part right here, secant theta tangent theta, when you see the integral of that, you should be thinking in your mind, okay, the derivative of something is secant theta tangent theta. And we all know that that's just secant. The derivative of secant is secant theta tangent theta. So that means the integral of secant theta tangent theta is just secant. Now I did have a 4 in front, so I have to bring this 4 here. And I'm going to evaluate this from negative pi over 3 to pi over 3. Alright, so I can say 4 times, and just work that part out. So this is the secant of pi over 3 minus the secant of negative pi over 3. Okay, so how do I find the secant of pi over 3? You say, what's the cosine of pi over 3? Everybody knows that's 1/2. The cosine of pi over 3 is 1/2. Take the reciprocal of that. So that's 2. Minus. Alright, anytime you evaluate a trig function at a negative angle measure, or most times when I do, I use the even-odd properties. The even-odd properties for sine, cosecant, tangent, and cotangent say that if you take the sine, cosecant, tangent, or cotangent of a negative angle measure, that's equal to the negative of that angle measure evaluated at the positive of the angle. For cosine and for secant, if you take the cosine or secant of a negative angle measure, you can just get rid of this negative. It can go away. So the secant of negative pi over 3 is the same thing as the secant of pi over 3. So what's the secant of pi over 3? 2. Minus 2. So I have 4 times 0. 0. All right, so this is integration with substitution. First, I'm going to show you why we can't always just use the power rule. At least for a problem like this. Say that I had x squared plus 4 raised to the third power. If we tried to integrate this the same way that we would integrate, say, just x cubed, adding 1 to the power and dividing by the power would give me this right here. And so, if this is my answer, then that means when I take the derivative of this, I should get this over here, right? So if I took this right here and I took the derivative, that would be 4 times x squared plus 4 to the third over 4 times, then you got to do the derivative of the inside, 2x. And so you can see this is not the same thing as this. It's close, but it has this 2x right here. Or more importantly, it has an x to the first power that's on the outside of that, but it's not present there. So you can't do these just like the regular power rule. We have this other stuff that we're going to have to adjust for. Okay? Now actually, this integral that I have listed here, if you wanted to integrate that, believe it or not, the fastest way to integrate that is to cube that binomial and then integrate each term separately. Okay? However, let's say that we had the integral of 6x times x squared plus 1 to the fourth. Alright, so the first thing that I need to do is I need to identify a u. A u is going to be something that is of the variable nature that's being raised to a power, maybe in parentheses. It could be something that's under a radical. It could be an entire denominator. It could be a lot of different things. It could be a power. So a u for this problem, I don't have a lot of choices, but one of those choices is to let a variable u be equal to x squared plus 1. All right, so if I do that, what is the derivative of u equal to? It's equal to 2x. Now, this x right here, x to the first power, is present right here in the problem. Actually, to do this integral, this x has to be right here in the problem. If it's not, we can't always integrate it using simple methods like this, using substitution. Okay? The only other thing that we have to adjust for, we have the x, that's present. That's good. The only other thing we have to adjust for is the constant. If you have a constant in your du, or the derivative of your u, you bring out the reciprocal of the constant in front of the integral, or in front of your answer. So What's the reciprocal of 2? 1/2. You already have a 6 right there, so I'm going to bring it out front. That's 6 over 1, so I brought it in. I'm going to bring it in front of the integral. Now, this du right here is present right there. Alright. Now, I let this stuff in here be my u. So this is u to the 4th. And now I said this right here was present. So the du now is there. This x is in there, in this du. That is put there. Letting u equal the stuff on the inside of these parentheses because it was raised to a power will now allow us to rewrite the integral in a simpler form, and now we can follow the basic power rule. Alright, so that's equal to, that's going to be 3 times integrate u to the 4th with respect to u. So that's u to the 5th over 5 plus c. Now the only thing we have to do is plug the u back in. So this is 3/5 times x squared plus 1 to the 5th plus c. Alright. Let's say I had the integral of the sine of 4x dx. So this looks very similar to what we were doing before, but remember before we only had x, we didn't have 4x. So for a problem like this, your u is equal to whatever you're evaluating your trig function at. Okay? So if that's your u, what is your du? 4. Notice there's no variable beside this. Notice there's no variable in front of the sine of 4x. That's good. It has to be like that. The only thing that I have to do is adjust for this constant right here. So I'll bring out a 1/4, and now I can rewrite my original integral as just the sine of u du. Remember, I let u equal this 4x here. Now, we all know that the integral of sine of u would be negative cosine of u. So this is 1/4 times negative cosine of u plus c. So I need to plug my u back in. So that'll be negative 1/4 cosine of 4x plus c. So if I was to take this answer right here and take the derivative of it, I will get sine of 4x. Let me show you real quick an integral that we couldn't do because the du doesn't match up, that we could not do like that. If I had the sine of the integral of the sine of x squared, I could not do that using the method that I just did, because my u would be x squared, so my du would be 2x, but I don't have this x, and I can't bring out a 1 over x. It doesn't work like that. To do this integral, there would have to be an x in the front. There's not an x in the front, so we can't use that method. We would have to do something different. Alright, look at this integral. The integral of x squared times the square root of x cubed plus 1 dx. So I see a couple things going on here. I see something under a radical, and I see an x squared in the front. So let's let what's under the radical be our u and see if what's on the outside is our du. So let's say u equals x to the third plus 1. So du is going to equal 3x squared. Now look, this x squared and this x squared match up. That's good. That x squared has to be there in front of the radical. Alright, the only thing we have to do is adjust for this 3. The way we do that is we bring the reciprocal out. Now I can rewrite the original integral. This is 1/3 times the integral of, now let's be careful, we let what was under the radical be our u. So this is u to the, what does square root mean? 1/2 du. We let all the stuff under the radical be our u. We found our du. The variable on the outside matched up, so we can use this u substitution integration. So now, add 1 to the power, so that's going to be u to the 3/2, and divide by that power, 3/2, plus c. Or 1/3 times what? 2/3. So that's going to be 2/9 times, what did I let u be? U was x cubed plus 1. Raised to the 3/2 plus c. The very important part is that this and this match up. If this integral is x times x cubed plus 1 dx, this wouldn't work because that's x and that's x squared. If this integral was x cubed times that, it still would not work. Not using this method, we would have to do something a little different.